Chapter 13 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 13. The Manchester Ship Canal. A stranger dropped suddenly among the quays and wharves of Manchester, seeing around him the great ships upwards of 9,000 tons burden, great cranes unloading cargoes, and hundreds of wagons and railway trucks receiving the same from towering warehouses, would at once exclaim, surely this is not far from the salt sea waves, and might imagine that the breezes rippling the broad expanse of water before him are blowing fresh from the open ocean. But let him board yonder vessel, just casting off her moorings for an outward voyage, and follow her fortunes for a few hours, and he will understand that the road to the true home of all this shipping is a long one, and that Manchester has lured these shapely masts and smoking funnels far into the heart of old England by a waterway that stands among the foremost of the world's engineering romances. Let us accompany our passenger, and through paper and ink see what he sees. As we pass by the long wharves lining the water, the channel gradually contracts to a width of some 250 feet, but widens to 400 as we approach the mowed wheel locks. These are two in number, the one 600 feet long by 65 broad, the other 350 feet by 45. Our vessel enters the smaller, and in 5 minutes has descended 13 feet towards sea level. We proceed for 2¼ miles over what was once the bed of the Irwell, until our attention is arrested by a curious sight. A barge, borne aloft in mid-air, and a gigantic iron trough, known as the Barton Swing Aqueduct. How did the barge get there? Look to left and right, and you behold, far above canal level, 2 iron gates. Behind these the Bridgewater Canal is pent, while a section of it is calmly swung round, also enclosed by shutters at each end, with its floating freight that we may pass. As we drop into Barton Lock, the hydraulic machinery on the mid-channel pier slowly brings the trough athwart our pathway, and in a few minutes the bargeman is urging on his horses en route to Worsley. The country north and south of us is studded with the numerous towns that make this the most thickly populated district of England. Had we but ears to hear, the whir of innumerable spindles would speak to us of the great cotton industry of which Manchester is the heart, and into which the canal is pouring the lifeblood of commerce, to be distributed by the lesser arteries and veins of waterway and railroad. A few miles, we slow up once more for the passage of Earlham Lock, which lowers us another 16 feet, and when freed we pass under a great railway bridge, and note on our left the entrance of the Mersey into the canal. Our voyage is unbroken for 7 miles. Inland-bound vessels pass us at a stately pace of 5 to 8 miles an hour. There is no need to make for a siding to give the other room, as the canal has a generous width, 120 feet at bottom, increasing to nearly double near the locks. At Rixton Junction, the canal leaves the riverbed, and becomes purely artificial for the remaining 24 miles of its length. At Latchford, 14½ miles from Manchester, we again enter a lock, and drop from comparatively fresh into salt water, for at certain states of the tide no barrier is interposed between Latchford and the sea. We are now 60 feet lower than our starting point, having descended in 4 bold steps. Sailing with a straight course, we come to Runcorn, an important town on the now broadening Mersey. The river is within a stone's throw of our boat, but it will be a long time yet before we enter its waters. The canal now makes 2 sweeps, the first southwards from Runcorn, the second gradually northwards along the southern bank, behind great embankments dividing the canal from the river. Eastham reached, we pass the open lock, for the tide is up, and pass out into the Mersey at a point 35½ miles from the great cotton town. We may now glance at the history of this undertaking. As early as 1721, the necessity for efficient water communication between Manchester and Liverpool, then a rising port, caused Mr. Thomas Steers, an engineer of repute, to issue plans for canalizing the Mersey and Irwell from Warrington, to which small vessels ascended on the tideway, to Manchester. His scheme was carried out and subsequently extended to compete with the Bridgewater Canal, which united Manchester with the Mersey at Runcorn. The canal then absorbed the Mersey and Irwell navigation in 1844, and the two became formidable rivals to the railways. And finally, in 1886, both were transferred to the Manchester Ship Canal Company, for the sum of 1,712,000 sterling, a sufficient proof of their importance. The first scheme for constructing a ship canal was mooted in 1825, when a company was formed to unite Manchester with the Dee by a canal 51 miles long containing 14 locks. It came to nothing, however, sharing the fate of two later proposals, the second of which deserves short notice. In 1840, Mr. Henry Palmer drew up a plan for the Mersey and Irwell Navigation Company. For deepening the existing waterway sufficiently to pass vessels of 400 tons burthen into Manchester. By means of training walls built in the river above Runcorn, he thought the concentrated scour of the tides might be compelled to keep open a channel with a minimum depth of 10 feet. Locks and weirs would be established in the upper river, so that ships of the size mentioned could all reach Manchester except those with fixed masts, which would be compelled to discharge cargo at Barton, where the Bridgewater Aqueduct crossed the course. In 1882, the question was again taken up, this time with great energy. 70 leading Manchester merchants and manufacturers instituted surveys and reports on the feasibility of constructing a navigation to Manchester available for ocean-going vessels. Mr. H. Fulton and Sir E. Leader Williams undertook the surveys. The former was in favor of a tidal canal all the way to Manchester, where the rise of the country would necessitate a basin 90 feet below the level of the town. His colleague, however, spoke for a locked canal above Runcorn, on the grounds that the cost of excavation would be far less, and that the presence of locks would convert the river into a series of practically still water pounds. The latter plan was accepted by the company, which in 1883 introduced a bill into Parliament for constructive powers, but the application was thrown out by the House of Lords after passing the committee of the House of Commons. When introduced again the following year, the lower house in turn rejected it, but on a third attempt in 1885 the company gained its ends after the costs of introduction and opposition had amounted to 250,000 sterling. The committees left their mark on the bill, however, for the act demanded that for the training walls in the Mersey should be substituted a semi-tidal canal along the Cheshire side of the estuary, entering the Mersey at Easton, 6 miles above Liverpool, whence a good low-water channel led to the deep waters. After some hesitation on the part of the Lancashire financiers, the necessary capital was subscribed, and the late Mr. T. A. Walker, of Severn Tunnel fame, obtained the contract for 5,750,000 sterling. On November 11, 1887, the first sod was cut at Eastham. On May 21, 1894, the late Queen Victoria formally declared the whole canal open to traffic. This titanic work necessitated the excavation of 54 million cubic yards, nearly a quarter of which was sandstone rock. At the busiest period, 17,000 men were engaged, aided by 80 steam navvies and dredgers, 316 steam engines and cranes, 173 locomotives, and 6,300 wagons and trucks running on 228 miles of temporary railway, the value of which plant approached £1,000,000 sterling. The cost of the canal, including construction of works, the purchase of lands, 1,289,000 sterling, purchase of canals, 1,786,773 sterling, parliamentary expenses, general expenses, surveying, etc., amounted on January 1st, 1897, to the huge total of 155,168,795 sterling, 15 shillings 11 pence. A sum greatly in excess of what the promoters had originally contemplated. It must be mentioned, however, that as the work progressed, the scheme enlarged itself in the direction of greater dock and warehouse accommodation, etc. The untimely death of Mr. Walker in 1889, by throwing the contract onto the company, involved it in considerable loss. As often happens in great engineering feats, the unknown quantity of unforeseen natural obstacles, such as faults in the strata excavated, and heavy floods, pressed hard upon the contractors and promoters. In 1890 and 1891 winter floods worked great havoc with the cuttings. One cutting, in the Earlham division, was almost completed when the natural dam at the Manchester end, shutting it off from the river, suddenly gave way under the pressure of the spate, and in 10 minutes over 250 million gallons of water had rushed into the cavity, bearing with it more than 100,000 cubic yards of material. When the water had been pumped out, under cover of a new dam, trains of wagons were found tied up in knots, and heavy machinery scattered far and wide. During the 2 years mentioned, No less than 23 miles of cuttings were filled prematurely by water, which had, of course, to be pumped out before work could proceed. Retracing the course of the canal, we will remark upon its most noticeable engineering features. Throughout its length, excavation was needed, but in varying degrees. From Eastham to Runcorn, the level of the estuary at high tide being equal to or greater than that of the mean level of the canal, embankments were necessary for long stretches. Between Runcorn and Latchford, where tidal action ends, the canal leaves the river and enters higher ground, necessitating cuttings from 40 to 70 feet deep. From Latchford to the junction with the Mersey, again, the cutting is continued, but from the latter point to the confluence with the Irwell, embankments once more are employed to keep in the water. The upper reaches of the Irwell required further cuttings 30 to 40 feet deep. The depth of the water is kept by the locks at 26 feet throughout, the gates at Eastham being closed as soon as the tide level of the estuary has fallen to that height above the bottom of the canal. During the flow of the spring tides, the opened gates permit a greater depth up to Latchford. A peculiar feature of the canal is the rapidity with which the tides work up to Latchford, where, at high spring tides, the level is raised to 9½ feet above normal about half an hour after high tide at Eastham, 21 miles farther down. Within 2½ hours of high water at Latchford, all this extra volume has again left the canal. The result is a strong current, which in turn entails the lining of the canal side with stone facings, which also have to withstand the scouring action of the ship's wash. The latter consideration has indeed made such protection necessary throughout the canal, except in a few places where natural rock is met with of sufficient height. In the Eastham division of the canal, 3 large embankments were made, known as the Pool Hall, Ellesmere Port, and Ince Bay embankments. The method generally employed was to tip 2 parallel mounds of rubble on the foreshore to act as toes, or supports, for the lower edges of the embankment slopes, and then pile between them mounds of stiff clay. At some points the engineers encountered great difficulties, owing to the pressure of a substratum of mud or sand through which the estuary water forced its way to the workings. In Ellesmere Bay, especially, for a distance of 1 1/5 miles, a particularly staunch protection was needed, for although at that time the deep channel of the Mersey lay on the north side of the river estuary, it had formerly passed close to the southern bank, and might return thither again. Accordingly, for 5,400 feet, 2 parallel rows of piles, 1 foot square and 35 feet long, were driven down contiguously into the sand so as to form 2 wooden walls 78 feet apart, the summits of which were at the bottom of the embankment. To make these subterranean walls the more secure, 2 additional rows of piles, shorter and 6 feet apart, were sunk to the same level at distances of 20 feet from the inner row and 25 feet from the outer row, and anchored to the sheet piling by stout cross timbers. The driving of these piles, which represent a total length of 100 miles of foot square balks, would have been practically impossible, not to say ruinously expensive, had force only been used. Recourse was therefore had to the erosive action of the water jet, a device that has proved of immense use in many undertakings. A jet of high-pressure water was pumped by steam engines through a pipe of 1½ inch bore and 40 feet long, which preceded the pile in its downward course, softening and loosening the sand to such a degree that the pile easily pierced the stratum. 21 pile drivers were kept at work, the best week's record being 554 piles sunk into place. As the rows lengthened, a trench 15 feet deep was excavated behind the piles for an average width of 12 feet, and immediately filled in with rubble and clay in equal amounts. This gave a firm and watertight foundation for the superimposed embankment. At intervals, cross dams were built from side to side of the canal, so that the failure of one part of the embankment should not flood the whole of the works. Just below Runcorn Lock, a concrete wall 4,300 feet long is substituted for earthwork. The wall is founded upon sandstone rock at its extremities, the central portion resting on gravel. It has a bottom breadth of 22 feet, tapering to 16 at the summit, which is about 40 feet above the foundation. The vertical side facing the canal is protected from damage by timber fenders. This wall is in itself a large and costly piece of construction. So well have the engineers done their work that after several years the walls remained staunch and sound in spite of severe storms. Some of the most difficult portions of the canal are included in the Earlham Division, which extends from the 26th to the 30th milestone above Eastham. The cutting here is deep, and as the line of the canal crosses the beds of the Mersey and the Irwell many times, construction proceeded in short lengths across the bends, the river being allowed to pursue its natural course until each chord was completed. The dams at either end were then cut, and the arc of river turned into the artificial channel, the dried bed being filled in, the spoil of the excavations. The strata of blue clay, gravel, and alluvial deposit were of such a nature as to cause the sides of the cuttings to fall in, and sometimes entirely bury the steam navvies and other plant employed in excavation. At one place a slip was burnt and replaced in the hole made by its subsidence, but as a rule the slipped material was cleared away, and lumps of rock and quarry rubbish substituted. Most of the excavating was done by steam navvies of English, French, and German design. The English machine is stationed in the bottom of a cutting, and works a great ladle attached to the end of a beam, scraping up the side of the cutting until the ladle is filled with its load of 1 to 2 tons of material. The arm then swings round, deposits the spoil onto a truck. The foreign patterns resemble ordinary marine or river dredges, the earth, etc., being collected by an endless chain of small buckets, working round a boom which is gradually lowered into the hollow eaten out by the buckets. The French navvies proved particularly useful in light soil or soft clay. The English would make deal with all sorts of material, including blasted rock, which defied the other types. Apart from the dry excavating, these machines were serviceable, as the English navvy could easily be converted into a 10-ton crane by the removal of the ladle, while a slight alteration of the French excavator fitted it for work under water. Thanks to these powerful allies, the rate of excavation attained 250,000 cubic yards a month in the Earlham Division alone. Even when rock was handled, the total for the same period reached 100,000 cubic yards. In several places, the excavated material was used in the deviations constructed to carry the railroads that crossed the canal at various points. The interruption to passenger traffic would have been so great had opening bridges been employed, that the canal company adopted high-level viaducts, the underside of which was 75 feet above the level of the canal. In order to preserve a gradient not exceeding 1 in 135, embankments of great length were unavoidable, and their construction cost the company no less than 875,000 sterling. There are 4 railroad deviations, one at Warrington to carry the London and North Western and Grand Junction lines, another at Latchford for the Warrington and Stockport Railway, a third at Earlham, and a fourth at Cadishead, these last 2 for the Cheshire lines. The girders spanning the canal vary in length from 150 to 300 feet according to the angle of their crossing. 9 important highroads also had to be given a passage. At Warburton and Latchford, small additions of the 4th bridge afford a permanent means of communication at the same height as the railway viaducts. The remaining 7 are swing bridges revolving on masonry pillars, with spans ranging from 75 to 140 feet. The Moor Lane Bridge may be taken as typical. It is 238 feet from end to end of the span, the longer arm 240, the shorter 98 in length. The main girders are 27 feet 8 inches deep at the center, diminishing to 6 feet and 8 feet 9½ inches at the extremities of the arms. These girders rest on a square of cross girders attached to the upper roller path. A live ring carrying 64 conical rollers separates this from the lower roller path on the top of the masonry pier. The whole is swung round by hydraulic machinery. The most interesting feature of the canal is undoubtedly the Barton Swing Aqueduct, to which allusion has already been made. The Bridgewater Canal, built in the 18th century for the Duke of that name by the famous Brindley, connected the Worsley coal fields with Manchester, and subsequently Manchester with Liverpool. The canal was, and is, considered a wonderful feat on account of the bold project, successfully carried out, of its engineer to keep it absolutely free of locks into Manchester, by raising embankments and viaducts, and cutting tunnels wherever the ground fell away or natural obstacles intervened. To cross the Irwell, he built a stone and brick aqueduct, which was the first of its kind, and one of the 7 wonders of its time. When the Irwell became in turn a canal, The question arose how one waterway should cut the other. The smaller must of course give way to the more important, but the construction of locks from the higher to the lower level would entail a waste of water which the Bridgewater supply could not make good. Sir E. Leader Williams met the difficulty by a conception as unique as that of Brindley. The canal should not have its level interfered with, but a section of it should be bodily moved out of the way of passing steamers. The masonry was pulled down and replaced by an iron trough resting at its center on a pier rising in mid-channel. The following is a description given by its designer. The pier is mainly built of concrete, with brickwork and granite in the part that takes the weight of the aqueduct, 1,400 tons, including the water which is always in the iron trough through which the barges pass. The sides of the trough are 1 foot above the water level. It is carried by side girders 234 feet long, 22 feet 3 inches apart from the centers of the girders, which are 33 feet deep, tapering off to 28 feet 9 inches at the ends, with a side towpath carried on a gallery 9 feet above water level. Watertight iron swing gates are provided at each fixed shore end, and also at each end of the trough. When all 4 gates are open, barges pass along the canal as usual. If a ship is to pass through the aqueduct, all the gates are closed, the shore gates keeping back the water in the canal, and the other gates confining the water in the trough when it is swung open for the passage of the ship. The gates are worked by hydraulic power, as is also the trough, which can be swung with barges in it, the gross weight to be moved remaining the same. At each end of the trough, a watertight joint is made by an iron wedge piece of the shape of a cross-section of the end of the trough, both ends and bottom being faced with India rubber. The fixed and movable ends of the aqueduct are slightly tapered and about 1 foot apart. This vacancy is filled by the wedge piece, which weighs about 12 tons, and is lifted by 4 hydraulic rams sufficiently to allow the trough to be moved, the water between the gates being passed off into the ship canal. The junctions just described are not at right angles to the trough, but are slightly diagonal, so as to allow sufficient clearance for moving the trough. After it has been again closed, the wedge piece is dropped onto its seating, being of the same taper as the ends of the trough and aqueduct. The arrangement of the annular girders, rollers, etc., are the same as those for the heaviest swing bridges already described, but half the weight of the movable portion of the aqueduct is taken by a central hydraulic press, 4 feet 9 1/2 inches in diameter and 2 feet 3 inches deep, which acts as a pivot and is free to turn. A hydraulic buffer and locking bolts are also provided. The power is obtained from the adjacent hydraulic station, which is also used for the road swing bridge. The aqueduct has never given any trouble, working quickly and with smoothness, a result for which much credit is due to constructors, Messrs. Handyside and Co. Not many miles from Barton may be seen another remarkable instance of barges moved in closed troughs with the same object of avoiding lock wastage. At Anderton, some little distance south of Runcorn, the Trent and Mersey Canal meets the Weaver navigation at a point where there is a difference of 50 feet in their levels. Barges up to 100 tons displacement are transported from the one to the other by means of a double hydraulic lift, working vertically. 2 troughs, each weighing with contents 240 tons, are supported on 2 cast iron rams placed under their centers, the cylinders of which are connected by piping. When both troughs are full, the pressure on the rams is equal and no movement takes place. But on 6 inches of water being transferred by siphons from the one trough to the other, the heavier forces up the ram of the lighter. Similar lifts have since been constructed at Fontenelles on the New Fosse Canal in France, at La Louvière on the Central Belgium Canal, and at Peterborough on the Canadian Trent Canal. This last has a rise of 65 feet. The second transports vessels of 400 tons burden. Among the other chief features of the ship canal, we must include the Weaver sluices, the locks, and the Manchester docks. The River Weaver entered the Mersey about 2 1/2 miles below Runcorn. When the embankment was built between the canal and the estuary, the natural passage of the river was cut off, and it became necessary to provide means for letting the waters of the Weaver into the estuary in the same period of each tide as they would have passed into the estuary if the ship canal had not been made. Great sluices were therefore erected on the embankment on a platform of masonry 470 feet long, 3 to 4 feet thick. protected on both faces by sheet piles and stones against the undermining action of the water passing over. Steel caissons, 36 feet long and 9 feet wide, were built to the platform to contain the lower part of the piers between the sluice gates, which are 10 in number, each 30 feet wide with a lift of 13 feet. A bridge passing over the tops of the piers carries the winding gear, by means of which 2 men can easily raise the ponderous gates. Since the Weaver is practically the only route by which Cheshire salt can reach Liverpool for export, any derangement of traffic over the navigation would have spelt heavy losses to the salt mines and the British salt trade. Under the Ship Canal Acts, the company had to permit Weaver salt barges a free use of the ship canal to Eastham, unless their tonnage exceeded that of those previously used. Chemical and other traffic had to pay the usual tolls to the company. If the owners preferred it, however, the barges could drop to the Mersey at Runcorn or Weston Mersey locks. The locks on the direct course of the canal at Latchford, Earlham, Barton, and Mode Wheel are duplicated. A 600 by 65 lock lying parallel to one 350 by 45 feet. By means of intermediate gates, these can be subdivided into smaller lengths of 150 and 450 feet, and 120 and 230 feet respectively, so as to pass craft of all sizes with the greatest possible economy of time. Large culverts running along the lock walls fill the 350-foot lock in 4 1/2 minutes, and the other in proportionate time. Between the smaller lock and the southern bank of the canal, which doubles its breadth at the locks, is a weir pierced by 30-foot sluices to pass all surplus water. In flood time these are especially useful. On such occasions, some of the spate is discharged through the embankments into the upper reaches of the Mersey estuary. At Eastham, a third lock, 150 feet long, is added to the 600 and 350-foot locks, having their width increased to 80 and 50 feet. The cement used in the construction of the locks was subjected to severe tests, a notice of which may be interesting to those readers who are unacquainted with the properties of this material. The cement was tested 14 days after delivery. Samples taken from every 30 tons were first passed through sieves of 2,000 meshes to the square inch, and all cement rejected which left a residue of more than 10% in the sieve. Briquettes having a sectional area of 2½ square inches were then made and submerged in water for 8 days, at the end of which time their power to resist tensile stress was proved. The minimum permitted was a pull of 700 pounds. Some stood a stress of 3,000 pounds, or about 1 1/4 tons without breaking, but the average resistance was about 1,000 pounds. All cement used in the fourth bridge foundation had to undergo equally severe tests, for we read that the contractors required a briquette of 1 square inch section to resist a pull of 400 pounds at the end of 7 days. In fact, owing to the large amounts now used, cement for all important works is submitted to a rigorous system of testing and analysis before being accepted from the manufacturers. The Manchester and Salford docks, which commence at Mode Wheel locks, have an area of 104 acres, 152 acres of quay space, and a frontage of 5 miles. These figures are, however, only temporary, since new docks are in course of construction. Dock number 9 will alone have a frontage of over a mile, and dock number 10 will be of almost equal dimensions. The quays carry sheds and warehouses rising to 7 stories, and over 30 miles of railway sidings. They are equipped with steam, hydraulic, and electric cranes, and other appliances for quick dispatch. There is also a grain elevator of 40,000 tons capacity. That, owing to the huge expenditure incurred by the company, the shareholders of ordinary stock do not find their investments profitable, will be evident enough on reference to the quotations of the money market. At the same time, it would be a great mistake to condemn this magnificent engineering achievement as a commercial white elephant. We must remember that the ship canal is in direct communication with the whole of the inland navigations of the country, that the area to and from which the canal traffic is carted contains 2 1/2 million people, and that in the districts nearer to the canal than to any other ocean steamship port is found 1/5 of the population of the British Isles. A city far inland has become a seaport, with facilities equal to any on the coast, and this in spite of great opposition from rival interests and almost insuperable physical obstacles. Why? Because Manchester is the centre of one of England's greatest industries, which, owing to its natural position, was severely handicapped in competition with other progressive countries by the cost of transport to and from the ocean ports. If Manchester meant to hold her own, freights must be delivered at her very doors, unbroken, since breaking bulk often ate up the manufacturer's profits. The reduction in cost of transport and handling the 6 million tons of cotton imported annually into the Manchester district is amounted to 500,000 sterling, and the total benefit under this heading to the community may be reckoned at more than double that sum. A most eloquent testimony to the usefulness of the canal is the external change that has come over the face of Manchester. Previously to 1880, the city showed decided traces of incipient decay. Many large works were moving to Glasgow and other ports, where they could save the excessive costs of carriage. Empty warehouses boded the migration of trade. Since the opening of the canal, new industries have started at the terminus and along the banks. The deserted mills and warehouses again teem with life. Miles of new streets have been laid out, and renewed activity is seen on all sides. The traffic returns increase steadily from year to year. In 1896, the whole receipts of the Ship Canal Department were 182,000 sterling. In 1902, they had risen to 358,491 sterling, or nearly double. In 1896, the profits were 65 sterling. In 1902, 140,955 sterling. These figures show that though large accessions of traffic bring an increase in expenditure, that increase is not in proportion to the tonnage. The directors of the company do their utmost to encourage merchants to use their canal. Already suggestions have been made for deepening the canal a couple of feet to accommodate vessels of 11,000 tons capacity, double the size of the largest cargo steamer afloat when the act was obtained in 1885 for the construction of the canal. Established lines of steamers ply between Manchester, America, the Mediterranean, and other parts of the world. As recently as 1903, a regular fortnightly service was inaugurated with Boston, and the number of monthly sailings steadily augments. Whatever may be the future fortunes of the canal, nothing can detract from the public-spirited policy that brought it to completion, or from the skill and perseverance of its engineers. When Macaulay's New Zealander of the future has wearied of gazing upon the ruins of St. Paul's from the broken arches of the London Bridge, he might with profit turn his steps to the north. We feel confident that after a journey from end to end of the canal, even if its channel has silted in, and its locks and wharves have fallen into decay, his verdict will be, the people that did this work must have been a mighty race. End of chapter 13.